So in the last video, I talked a lot about what we're going to do and why we're going to do it. Now let's talk about how we're going to do it. All right, so we're going to use our first technique for estimating something like square root of 105 is called linearization. So linearization works like this. Think of a graph. So if I think of a graph of the function that I'm talking about here, I want a functional value of 105. So think about the function f of x equals square root x. So when we estimated it, we used the fact that we knew what a certain square root nearby was. We knew that the square root of 100, we know what the square root of 100 is. We just don't know what the square root of 105 is. All right, so the idea of using a nearby known value is crucial to this linearization process. So I'm going to look at x equals 100 because that's near 105 and I know what that value is. So essentially what we're doing is we're saying, okay, I know what the square root of 100 is, it's 10. If I want to know the square root of 105, now this again points out also to how I considered f of x being an increasing function, so I know that the value of square root of 105 is going to be more than 10. So what we want to do is sort of formalize this graphical process and improve our estimate. All right, so what I want to, here's what essentially we're going to do. We're going to say, look at the tangent line at this point, and we can't follow the function because we don't know what the function value is, but the tangent line is just linear. It has a slope and a y-intercept, and I can work with those easily. And the value so if I just follow up the tangent line, the value we hit is going to be very close to what the actual function value is, depending on what the function looks like. All right, so let's look at a zoom of that. Zoom in on that a little bit. So what's happening, between x equals 100. So here's x equals 100. So this is a point 110, right? And then this point over here is the point 105 square root of 105, which we don't know what it is. But then what we're going to do is we're going to follow the tangent line instead of the function. So you can see that what we're going to get is not going to be the same number in this picture where I've greatly exaggerated the relationships. However, in this picture, you can see that, yeah, actually it's the estimate is going to be pretty close to the function value. So here I'm just exaggerating so we can see the difference a little bit better. All right, so this point over here is going to be 105 something. Let's just call this point, let's think of this point down here as being x1, y1. And we'll just say that for now this point up here is x2, y2. And we're going to use this y2 as an estimate for our square root of 105, whatever that y2 is. Now by using x1 and y1 and x2, y2, I've given a hint as to the direction that this is going to take, especially since, as I've said many times, in calculus, everything comes down to the slope formula. So that slope formula that you learned in 5th grade, m equals y2 minus y1 over x2 minus x1, that's the starting point for this. So then, one thing you can do here is multiply both sides by x2 minus x1 and get y2 minus y1 equals m x2 minus x1. And by the way, that's the point slope form of the line. Where does it come from? It comes from the slope formula. All right. And then what we're going to do is sort of work with this a little bit, to work with it algebraically, because what we're really interested in is this y2. We want to use it to estimate. So let's solve for y2. So y2 equals m x2 minus x1 plus y1. Okay. So now all we're going to do is rename things. So we're going to call x1. So x1 is an important quantity in terms of the problem. What this x1 is, it was a point nearby to the point I wanted to know, where I know what the functional value is. So it's a nearby known value. We're going to call that a throughout this work and much other work. So then the y1 is f of a. All right. Now, this function up here, we're going to call this x2 value. So these x values are the same, and they're the 105. So the number in here, we're going to call that x. We're going to be pretty consistent about calling that x. And this y2 is approximately equal to f of x. So really, this is the point x f of x. This is the point x approximately f of x. All right. So Now let's also think about the m. So the other thing that we know about this picture is that the slope, m, is just f prime of a, because this is the tangent line at a. So the slope is f prime of a. And that's enough for us to just write f of x. So the y2, we're going to call it f of x, is approximately equal to, right? Because y2 is approximately equal to f of x. So f of x is approximately equal to this stuff, which is our m is f prime of a, and then our x2 is x. The x is the value we want to know. It's the square root we want to know, minus a, x1 is a, that's the square root we do know, plus f of a, so that's the square root of the number that we did know, right? So that's how we can get this from the slope formula. Normally, people write it with the f of a first. There's a reason for that, because it corresponds then to some of the more sophisticated methods that you're going to learn later. So we like to usually put the f of a first. All right. Another way that your book likes to write this, and it's a fair thing to do, is that they'll create a new function called L of x. And L is for linearization. So L of x, now f of x is going to be approximately equal to L of x. But L of x is this. So we say L of x equals f of a plus f prime of a, x minus a. And that's called the linearization of f at a. All right. Why linearization? Why are we calling it linear? Because this is a constant. F prime of a is a constant. So if I distribute the constant, I'm going to have mx plus b after I combine that with this. So these are all constants, right? So the power of x is 1. So this is a polynomial with degree 1. It's a linear function. So an important way to think of this is we've just created a linear function that is approximately equal to this nonlinear function square root of x. And an important way to look at this is we're taking nonlinear functions, we're coming up with a linear function that approximates that nonlinear function. So that's important because linear functions are easy computationally. So in the machine language programming or assembly language programming that goes into a mathematical program, essentially the operations you have available to you are add, subtract, multiply, and divide, because those things can be translated into logical operations on binary numbers, okay? But finding the square root of x cannot be translated directly into a single step logical operation on a binary number. So there has to be an iterative process that essentially relies on linear functions. The computer can only calculate linear functions, essentially. And so we're going to use this linear method to approximate this nonlinear function, and then we'll find ways to make that more sophisticated. So at this point, this is all very abstract. We'll use it to actually estimate square root of 105 next.